So I want to talk about two things that have confused me about neural networks for quite a long time. Yeah. I'm hoping that by the end of this time, you'll be as confused as I am. And what I'm going to cover today is a number of different things depending on how I take a long time. So I want to first of all talk about generalization, which is basically why do they work so well. I want to look at two different questions of that. And I'll look at one particular inductive bias towards simplicity, and if I have time, particular kind of Zipf's law inductive bias as well. And then I want to talk about feature learning. And as we go down, I understand these things less and less and less and less. By the end, I don't understand it at all. So just to remind you, this has been said already by a number of authors, but I thought I'd just put this picture up for those that haven't seen this before. So a very famous paper back in 2016 from my group at Google, called Zhang et al., did the following experiment. They took a bunch of images, they randomized the labels, and here you see the loss as a number of SGD steps. And this is for like true labels that converge quite quickly, but even for completely random labels, this was able to train to zero training error. And so their paper was understanding deep learning requires rethinking generalization. I think actually we knew already then that neural networks are hugely expressive. That means they can basically explain almost any kind of data. In this case, this would be they have very high capacity, we've been saying if you're a classic machine learning person. So that ability to learn randomized labels is a well-known capacity measure, Rademacher complexity. It's a very high Rademacher complexity. We knew that. So actually, the surprising thing in this paper isn't at all that you could learn random labels. The surprising thing was that SGD was really good at finding that solution in a relatively short amount of time. The question that obviously raises, if you could just memorize the labels, then why don't neural networks do that? Why don't they just memorize labels and then not generalize at all? Why do they pick solutions that generalize well? And that can be, what the point of this is also that these are highly overparameterized systems. So they're systems with a very large number of parameters, more than the number of images in this case. And for physicists, this should make us very nervous. So as Shivaji pointed out earlier, there's a famous quote, it's actually by Fermi, who quotes von Neumann, it's Dyson who tells a story. It's a lovely little article here called Meeting with Enrico Fermi, where Dyson talks about going to Fermi with this very exciting theory he has. It's a particle theory that's Lucas Drax, if I remember right, had 5 parameters. So basically, he took a bus from Ithaca all the way over to Chicago to see Fermi, tell him about his great theory. And then Fermi said, well, with 4 parameters, I can do an elephant. And with 5, I can make it look at its tail. And this is deep in physics. We taught this from a very young age. Don't use too many parameters because you're going to get nonsense. And in fact, a number of years ago, a group showed that, in fact, with 5 parameters, that as usual, Fermi was right about these things. So it turns out that with 4 parameters, you can't make an elephant. With 5, you can make it. With 5 complex parameters, you can make it strong. So that quote gives us an intuition for how we would expect these things to work. We shouldn't use way more parameters and data points, or we're going to get nonsense. That's the idea. And here's a very simple example of this. So I give you these 10 data points, and this is what we do for our first-year undergraduates. We give them data points, tell them to fit a function to it. If you fit a 5th-order polynomial, okay, you get something that kind of interpolates, can't quite get the data right, but does we think intuitively reasonably well. I fit a 20-order polynomial, I can exactly fit the data, but I get these wild oscillations. This is what we teach undergraduates. So don't use a 20-order polynomial, that's bad. So just showing you here, this green curve is actually a 1, 2, and 5 hidden layer neural network, with each layer having about 1,000 units. There's a large number, orders of magnitude parameters and data points. What's really surprising is this neural network fits this function to it. Okay, a neural network, by the high expressivity, could have easily fit this polynomial, or almost any polynomial you can imagine, including almost any function that's integrable with some few constraints on it can be fit by this neural network. So there's no a priori reason why it picked this solution that one can see over an infinite number of other solutions that it could have kept. And the question is, why did it do that? Because I think this is one of the really surprising conundrums of neural networks. So we see this all the time. So I've got here a picture of our esteemed colleague, who's basically been working on knot theory. And what he and his collaborators have done is show that you can train a neural network on things that we know about knots, and they do extremely well at predicting very subtle, complex topological questions, including some of the big questions in knot theory. And this is completely mystical to me. So why did this work? I don't know. I like this. I thought this photo made you look sufficiently confident, and like this is on the Northeastern public webpage, so I can see how I'm going to solve this problem. We're going to do it through a neural network at it, and it works. I was completely mad that this would work. And so in physics, as I was walking up and down our open plan space, it was great. I discovered that Andre Lucas and his collaborators, Andre and others, were using this to learn all kinds of properties of Calabi-Yau manifolds. They train on a number of things, and then they predict extremely well. And it's completely utterly surprising. It's basically the category, why does your neural network give you something that predicts truth about knot theory or truth about Calabi-Yau manifolds, or name the other place where it's been applied, right? In hydrodynamic flows, I have colleagues that apply this for hydrodynamics. Why would the solution that you give a neural network reproduce Navier-Stokes equations when it could reproduce almost anything given the data? This is completely utterly mysterious. I don't understand this at all. And I'm just giving you one example here. So I'm going to have you come into the talk a few times. So this is really mysterious. Very mysterious property. Physicists should be looking at this property because it's telling us something very profound. It's telling us that somehow neural networks have this inductive bias towards picking very specific functions given data that recapitulate something very profound and deep about the natural world. So, is there anything you take from this talk? This is the main point I wanted to make. This point. This is a mystery, deep mystery. And the interesting thing about neural networks and machine learning, this whole modern open parametric machine learning world, is that it's telling us that there's something about the world that we look at, things that we're interested in, whether it's texts or images or physics or mathematics, that is somehow recapitulated by the inductive biases of these. So how do we understand these inductive biases? Well, if you go to, even here now, an undergraduate class in machine learning, this is perhaps the most iconic texts by actually 2 colleagues of Zohar's. And this is understanding machine learning. And if you look at this, there's a long history of very smart people, mathematicians that worked on this. And effectively, what they did is they formalized this idea that if you look at your risk, which is the error that you make as a function of the complexity of your model, which they call capacity, then there's kind of a sweet spot between making it too complex and you fit noise, or else what you get is that every time you fit it, you get a slightly different function, so you get lots of variance in your outputs. Or you can't underfit it here, and in between, you get it right. So for our polynomial example that we give our students, we say, get 10 data points, don't fit a 20-order polynomial because you'll fit almost anyone will fit because you get a lot of variance. Don't fit a 2-order, like a quadratic function because that would be too simple. Fit something in between. That's where you get the best prediction. That's our intuition. And this has been formalized in learning theory. But of course, what happens in practice in neural networks is that we're not in this regime. We go to really, really high capacity. And this is a famous double descent curve that Misha Belkin popularized. So as you keep it going, at first your errors go way up. Okay, when roughly at the point when the number of data points and the number of parameters very crudely are equivalent to each other, you get the worst possible error. And then after that, you get this modern interpolating regime where you do much, much better. And this is where Jim is sitting in his work. So the question is why in that open parameterized regime this is working? And one interesting thing is that this whole classic machine learning apparatus, which has been developed over many, many years, decades of hard work, doesn't apply, as far as we can tell, in this regime for various classes. So you have to kind of throw that book out. And so one question we can ask ourselves is, what would be right now if we wrote a textbook like this for over parameterized systems? Good point. Yeah.
Supposing I literally use polynomials and points, is it really true that if I use 100th order polynomial, I would?
Yeah, so roughly speaking, yes. If you start using really high, if you just linear regression, basically, it's a long story which I won't get into today, but people have looked at this recently, and even linear regression, very, very high things with like 1-2 traits works already really well.
We had a summer school a few years ago where Pankaj Mehta was there,
yeah.
And he has done a lot of things in deep learning over the years. And one of the things he wanted to do was show that you get double descent even for polynomial regression to really prove it. And that part of the classical part of learning theory, I think his point was not just that they, it wasn't that they weren't using neural networks, which was true a very long time ago. It's that they just weren't using enough parameters. They were not in the over-parameterized regime, and even appropriate polynomial regression in the over-parameterized regime exhibits stuff like this.
It's not the nonlinear stuff in there where you want all of that sort of stuff.
Well, maybe I should take a step back and say two things. First of all, there's been a lot of very recent work here that has shown some of this. Actually, if you look at Zohar's review on field theory, there's a whole section in there about kernels, which are generalization of linear models, and what makes sense. So actually, we do understand this much better for these simple models, and we understand what they're doing. And what they're basically doing is, if you go to these the story that's emerging right now is if you go to these very highly parameterized models, you can think they typically you fit to a small number of important eigendirections that you learn. And then the rest of those little coefficients that you're not really using, they end up actually making what benign overfitting. They basically pick up the noise in your data and kind of capture it without going up. And so you get this kind of set of, you have these kind of main knights who are your heavy modes that learn the function. It's a small number, the effective number is relatively small. And then it's actually good to have these all this higher order noise because they kind of clean up the noise and make you not fit to the noise. That's the kind of emerging argument. And actually, the Funkos Mehta papers and a whole series of papers show that works even for just a linear regression. So there's a famous paper by Paul Bartlett called benign overfitting in PNS.
That's just shifting what we're starting to so just PhD thesis is going to work with Nathan Andre and exact solutions. So this morning suggested a somewhat different intuition, but not quite. But he made this point that the way you trained, you sort of head, towards you don't move in directions in which the elephants would wiggle too much. But that seems somewhat dependent on where you start, which is if you happen to start with a line over wiggles, you would preserve it. So that's a somewhat different intuition, which is
not quite, because these intuitions do work that they do depend on you starting close to the origin. Okay. And then these things work. If you start away from it, then it doesn't work. So it's a more subtle story. I would say that this stuff is now out there, and people that work on this for a while will understand it relatively well. I don't think it's quite actually it's interesting if anybody on the audience is keen, there should be a kind of pedagogical paper written on this over-parameterized simple system. But you don't need to do neural network, just into a parameterized regime. It's developing very quickly, and field theory might be one language that you can use it in Zohar's paper. That's this talk is based on. You'll see some of that being developed and some references to other people that have done that. It's all been in the kernel language. And that's very interesting for neural networks because you can map infinite width neural networks onto kernels. So that tells you really something about what neural networks are doing. And that's what Morris is trying to figure out this morning by saying, you look at initializations, you look at the kernel, which is basically what kernel doesn't learn anything, we just have a kernel when you start, and you use that to fit the data.
One thing to add is that Morris said that you get a minimal norm interpolating when you do that. And that's sort of related to the fact that you get an effective bridge, which is also a way of regularizing, which ends up being very similar. So it is consistent in that aspect.
So these things are all. So the fact is there is exactly. So there's actually look in Zohar's paper he talks about this practice. You get what's effectively like so normally what you do if you have way more parameters and data points, a normal thing, you add some kind of regularization. So you insist that, for example, the overall norm of all of the parameters stays small. And that's regularization. One of the ways is ridge regression. There's a number of different ways of doing that. This
assumptions would allow it to start with extremely random structure.
So those are things that you would do by hand. And what the claim is that in these hyperparameter systems, this kind of emergent property, the emergence. So it's lots of interesting stuff. All I'm saying is we're starting to understand this. I don't think there's not a textbook out or anything even remotely like textbook notes that really cover this maybe, but we're trying to get a handle on what's going on. And what's interesting is, in some sense, when I first double set came out, I couldn't really see what the fuss about it was because we know that under parameter networks do this. we know that parameterized neural networks work really well. The only question is there one peak between them or two? Or more, right? And it turns out actually you can fiddle with them in multiple weeks. And actually look back, lots of people knew about this over many years before. But again, this is a paper like that, technical paper. On the one hand, is obvious. On the other hand, it was really helpful and sharpening to everybody what they're looking at. And what it really did is for people that, like Michel Belkin, were trained in classical machine learning, it helped them realize that they're not in Kansas City laws, a different thing. And so that's kind of interesting. I would say, what these traditional machine learning techniques do is you try to typically calculate the capacity of your model. Then you try to make some kind of bounds, like how badly am I going to generalize on that? I just want to say one thing that we did work on this for. I worked on this with the students of mine when I first started this field. I spent a lot of time reading this textbook and trying to understand these techniques and simply apply them to neural networks. And we did write one bound. So just very briefly talk about something quite trivial, but just to remind you some Bayesian statistics. So the posterior that I train in a particular, or that I basically get a particular function given some training data S is the its likelihood times the prior probability in S divided by the marginal likelihood. So the prior function is just the likelihood that I get a function with F. If I then if I train to what typically neural networks, because they're all parameterized, you can train to zero training errors. So I have a bunch of images, I want to make sure I get all the images correct. Then that is equivalent to a likelihood that is given the data, it gives you one if the function is correct on all the data and zero otherwise. And then you get your marginal likelihood, which you sum, this is basically just this sum, if you remember, you sum over all functions of the likelihood times the prior. And that basically tells you that the marginal likelihood is the probability over all functions that you get zero training error multiplied by the probability of the function. So if you have some kind of learner with some parameters on it, then one thing the marginal likelihood is something like, if I give you a training set of, say, 10,000 images, how likely, on randomly picking parameters of my model, do I get zero training error? That's what the marginal likelihood is. So this is kind of interesting because it tells me if I have a model that has a good enough device, so it's likely to get zero training error, then my marginal likelihood would be big. And if it's very unlikely to get zero training just by randomly assigning parameters, then it won't do that well. So I can even take a neural network and just randomly pick parameters and ask myself, do I get zero training error? And if I do that long enough, then that will, on a particular set, the data set S, then that will be my marginal likelihood. And so what we showed with student Guillermo is that you can write a bound down using, so this is, I did this because I crossed out that book, but I'm going to step back and say it's not entirely nonsense. So there's a method called path Bayes, which is a classic technique in these bounds. And we worked on this, it's a function-based path Bayes. And you get a really beautiful simple result, which is the error. So this is the error that you get, the likelihood you get, the likelihood that you make an error is bounded by this log of the marginal likelihood. So this marginal likelihood measures the inductive bias, plus the little terms that don't worry about the little technical terms, divided by the number of data points. The more data points you have, the better your bound is. Idea. It doesn't scale as 1 over m because the marginal likelihood also becomes smaller as you get more and more data. The probability of zero training error goes down. And what I just want to show you here is that this is learning curves. That's basically what's your error as a function of the number of data points you have. For MNIST, which is just the numbers, all the way to C410, which is images. The top is basically for a whole bunch of different networks, from fully connected networks to ResNets to DenseNet to MobileNet, what our bound predicts. So that's basically as you increase more data, the error goes down, and you get this nice scaling law, the log scale. So you scale down. And the nice thing is our bound follows pretty well what these truly trained SGD trained neural networks are doing. So what this is telling you is that a neural network trained SGD with all the kind of bells and whistles on it is behaving globally very much like this model, which is trained at, which is that's going to be training it just our marginal likelihood. When we calculate the marginal likelihood here is we can't calculate directly for a real neural network. So we take the neural network, take the infinite width limit of it, and then you can take the Gaussian process, make some tricks, you can calculate that thing. So you can calculate the marginal likelihood. And then if you have it, you can put it into this classic bound and it describes something about neural networks. So the first thing this is telling us is something interesting, which is that Because what Morris is actually saying this morning, and I think one or two other people that spoke here have said the same thing. Because what happens at initialization is really telling you a lot about what the neural network is. These neural networks have inductive bias towards certain kinds of functions, and that is good bias for reasons that we don't understand, but it's good bias for images. Because just I take the neural network, I randomly pick parameters, and ask how likely am I going to get a good prediction on the images, it actually does much better than you expect in random chance. The other thing which I'll just notice, if you look here this is for CFAR, which is slightly more complex data sets, but actually the SGD looks like it's having one scaling law, and then it turns over to a different scaling law. I can come back to that in a minute. I'm going to claim that the difference here is actually what we call feature learning, which is a word that I'm going to try to define later in the talk. But it captures the difference between this kernel limit or this GP limits and so the interesting thing here is that I can explain a lot about neural networks without looking at SGD. And I point this out because there's a very, very large literature of people that focus on optimization and say somehow what neural networks are doing is very much determined by SGD. So you're asking yourself, what does SGD do? And here I'm showing you that I can, with a bound that doesn't know anything about SGD, I can explain some pretty interesting properties of how neural networks learn as a function of data sets. So maybe this is a bit too harsh to cross this out. Right? You did really say something. On the other hand, what have I really learned by writing down a complicated bound and putting all the complication into my marginal likelihood? All I've learned is that I need inductive bias to learn well, and that some things have better inductive bias than others, but I kind of knew that. So maybe I haven't learned it.
Sense they correspond to images from the real world, right? So
yes.
So if you look in, I don't know, Fourier transform, if you look at the nodes, then you have just a few frequencies which are important, and then I mean it's just big structures basically that appear in real world images.
Yeah, so basically, if you look at, so for example, the MNIST images are 784 pixels, so it's 784 dimensional space. But if you do like dimensional reduction, then you can show that the underlying data structure is something like between 10 and 14 dimensions. So it's much simpler. So they're not learning white noise, right? They're learning something much simpler. That's part of the story. I'll come back to that in a minute.
I guess must be if you take some other type of images, like I don't know, atlas images with very fine details that you have to be sensitive to.
Yeah. So let me get a little bit further. I'll come back to that question. I think it's a really good question. I want to actually not jump ahead. Right. So I want to also just make this is a very actually these questions about overparameterized neural networks, why they work well, is actually an old question. So here's a very famous statistician, Leo Breiman, famous for discovering or coming up with things like random forests, very popular methods. And in 1995, he wrote basically a little article, Reflections on Many Years of Refereeing for this journal, this conference now called NeurIPS. And he said a number of things that you could almost say today. Our field would be better off with far fewer theorems, less emphasis on faddish stuff, and more scientific inquiry and engineering. That requires real thinking, which I hope we're doing here. It's interesting that 30 years ago, that's what he felt. Now, for instance, there are many important questions regarding neural networks that are largely unanswered. There seem to be conflict discharge regarding the following issues. Why don't heavily parameterized neural networks overfit the data? Which is why do they work? That's the question. What's the effective number of parameters? Which is a related question. Why doesn't backpropagation head to Porto minimum, which is another related all the questions. Why do these neural networks work so well? He actually also called that article for model work, looking at Ising models, trying to look at simple models. So I just want to say that question is this very generic question. Why don't overparameterized neural networks overfit? I think I call that the first order question generalization. It's also true for kernel methods. Any high capacity methods, why does it work well? And that's a question which I think is different from the typical question that you care about if you're an engineer or practitioner, which is how do I get my particular neural network optimized? How do I pick the hyperparameters like learning rates to make it work? And I think that's a second order question. And I'm making that distinction because in my experience with referees, that they find it very hard to disentangle the first question, which is I think a question about a new theory of learning the overparameterized regime, which could be a textbook kind of thing, which holds for any including linear regression. So that's the kind of question that you have to answer. You have to explain why neural network work at all. And the second order question, which is super important if you're a practitioner, which is how do I get my neural network to work better than others? So in other words, if I have images, should I use an FCN or a CNN or a ResNet? Those are second order questions. So we're going to look at first order questions first. I thought I just this morning I'll get some quotes on what kind of theory often so I'm saying neural networks. So Boris Henry was more optimistic, but he said we should be realistic what it can do. Like you can't really do the theory of a jet engine, but you might have something about it. I think Zohar yesterday said deep learning is more like biology, which I think maybe we won't ever get a general theory. And this is Noam Shazir, who's one of the three people in charge of Gemini, which is Google's big large language model. There's billions hanging on this, so very clever guy. He says, he's asked why do large language models work well? He said, my best guess is the blind evidence. Nobody really knows what's going on. This is a very critical science. It's more like alchemy or chemistry was in the Middle Ages. So I'm hoping we can do better than that. But it's interesting that leading practitioners have these kinds of views at the moment. All right, so I'm going to look at one very, very simple Ising model-like problem that I've been working on for the last number of years, and I want to suggest this is it's a simple enough model that I can understand it, but very complex enough hopefully that it shows some interesting results. So let's say that you go to a doctor, let's say at a time of high pressure, and the doctor has to triage whether they send you to the hospital. And so this happened for many of us not too long ago. So if you ask the doctor might ask 7 questions, right? You have a fever, you have a cough, actually smell, or you're a bit older, you have heart problems, another comorbidities. And then the 1 means essentially to the hospital, and 0 means to the house. So in this case, everything's bad, there's a hospital. Maybe if you have the symptoms and comorbidities but are young, they might still send this doctor will send still in the hospital. But if you have the symptoms but you're otherwise healthy, they'll tell you to sit at home, etc. So the question would be, if I gave you a subset of these answers, could you neural network from that predict what the doctor is going to do on other sets of answers? Already from this explanation I gave you, you could probably make some extrapolation of what this doctor is going to do. It's interesting, there's only 7 questions, right? So there's 2 to the 7, 128 possible ways of answering that. So any one doctor will have 128 possible answers sent to the hospital. So the question would be, how many possible doctors are there? Well, there's 2 to the 128 possible doctors, right? So even for the simple question, already we've got 2 to the 128 possible solutions to these questions. That's 10 to the 38. It's a very, very large number. So the question is, if I just give you some of this data, you can't just guess because there's 10 to 38 possible doctors. You've got to learn something from the data in order to make a prediction of what the doctor's going to do on other data sets. And so what I'm going to talk about a little bit is something called a parameter function map. So use typical neural network, nonlinearities, or in layers. And the question is simply going to be, if I randomly pick parameters, what function is this neural network going to produce? And so on Boolean data, that basically means I give you random data, and I give you those 128 questions. Will the neural network send you to the hospital or not? Those questions. So which doctor is the neural network going to be? And there's 2 to the 128 possible doctors that they think produce on random samples. And because we think these things are highly expressive, we think they can indeed produce all of those. And so, neural network parameters, what we yes. This is a paper that's a few years old now, where we found the following. So we just randomly picked initial parameters with a few different ways, Gaussian, uniform, different Gaussians, how we pick the parameters. So it's basically the weights. They have some Gaussian spread or maybe a square spread. And what you find is something kind of interesting, which is if this was a truly random or a random, they would basically pick each of these with the probability 1 in 10 to the 38. What you find is that there are functions here that are found almost 10% of the time. And those turn out to be, perhaps not surprisingly, really simple doctors. So a doctor sends everybody to the hospital or nobody to the hospital. The symmetric on those two. Okay. And as you go down here, these are more complex doctors. So I haven't told you, I've got a complexity measure here, which I'm not going to get into, but it's basically just compression. So I take my string of what the doctor says, I ask how much can I compress it. I compress it a lot, that number is small. I can't compress it very much, that number is big. But what I see is that this network tends to predict doctors that have no compressions, or simply that you can compress them off. And you can typically compress something if there's some pattern in there that's learning. That's kind of interesting. What's also interesting is I actually just plot the probability that I find a particular doctor, and I rank them from 1 to 10 to the 38. Okay. I get this Zipf law-like behavior with no free parameters. I can tell, I know how many doctors there are, and it gives me the prefactor, and it fits exactly the Zipf law. Now, if I have time, I'll explain why I think that is. Now, what's also interesting is, now I can ask myself, which of these doctors will a neural network learn well on, which will they learn poorly on? So I've got that same x-axis here, which is the complexity of the doctor. And this blue line here is the neural network. Now, what you see is on simple doctors, or doctors that have a lot of structure in what they predict, I can learn relatively well. And then eventually, as the doctor gets more complex, I learn worse and worse and worse. On green here is just a random learner. So what I did here, what I explained to you is, what I did in this case is I picked 64 of the ulcers and asked the doctor, the neural network to pick the other 64. There's still, so if I give you 64 of the possible ulcers, there's still 2 to the 64 possible solutions that are consistent with that training set. So that's an example. There are very large numbers of functions that are training sets. A random learner just picks something random for the ones that it hasn't seen. Right? And that it always basically has a 50% accuracy on the doctor. But this neural network, for at least for simple doctors, does really well. It actually predicts 10% or 20% accuracy what the doctor's going to do on other questions for the wide range of simple. Now I'm going to talk a little bit more about how this function ordering with this tells us about which subsets of neural networks and very well. I also point out that this is SGD trained neural network. This is basically just randomly sampling to stuff like fiber. This is another example of where randomly sampling, no SGD at all, tells me something about what SGD is going to do. Right. So basically, Jim, you must be here somewhere. So I'll tell you. In the problems that you're looking at, somehow, if this is the inductive bias, then I think there's more inductive bias than simplicity, but this inductive bias must be telling us that these are problems that you're learning really well on. So somehow those problems in string theory are simpler. Yeah, that's the story. All right. All right, so why simplicity bias? Why is that there? Well, let's see what I'm doing. So I'm going to try to wave my hands a little bit and give you some physical argument for why you might expect something like this. And the first is that if I said to you, okay, how likely is that neural network going to produce a certain doctor that's just uniform over all doctors, so probably 1 to 38? That's a little bit like asking you to predict that doctor just by randomly sampling ones and zeros, right? That's very similar to monkeys on keyboards. So Borel's famous example of infinite number of monkeys on typewriters where they type something useful, or they may or may not. So this is an example from Rich Dawkins' book, The Blind Watchmaker. Turns out if you look, even for a normal monkey on a typewriter type out, methinks like a weasel, will take longer than the age of the universe. Probability is very low if they get all these things right. On the other hand, that's the monkey theorem. But you can think of a different monkey theorem, which is monkey that's typing into a computer program. So let's say into something like Python. Then the monkey might accidentally type a program like print 0, 1 50 times, and you get a long sequence of zeros and ones, or some other program. So if you think about what's the right analogy for my neural network, it's actually the second algorithm, if I can lie into the next wall. Because what I do in neural network is I flip my weights around, I pick my weights at random, or I try to learn my weights. But the weights are not what the neural network does. It's a function approximate, right? Neural network takes input and has a function on the input and puts an output. Right? That input could be pixels that it turns into a label, a categorical label like cat or dog, or it could be Boolean images, it could give a Boolean function that gives you basically it's a function approximation. That function is generated by this program, which you can change by randomly changing the weights. So this is a better analogy for what this does. Then the question is, can we say something more general about these algorithmic monkeys? And then I want to jump, so to do that, I want to talk about a really interesting piece of mathematics, computer science that I think physicists should be doing a lot more of. So that's why I'm putting it into physics. So I want to first talk about homo growth complexity or homo shaping complexity, which is the question of how do you calculate the complexity of an individual string. And intuitively, I give you this string 0, 1, 50 times. That is simple because I have some simple description of it. Whereas this string below it, as far as I know, has no shorter description than print the string. That's a complex string. And so their argument is the complexity of a string can be defined as the length of the shortest program that will generate that string on a universal Turing machine, which is a universal computing device. And the power of this is that it doesn't, first it will depend on which computing device you use, like it will depend on which language you use. But because you can always write a compiler from one language to another, asymptotically is independent of the language you use. This is a universal kind of thing. It's also very interesting because you formally can't compute it. It's a halting problem. So you probably remember Turing came up with the universal Turing machine not to invent basically the foundation computation, to show that there are things that computers can't calculate. And it's basically trying to show an algorithmic or computational version of Gödel's undecidability. And the way that works out in his computer is that there are halting problems. There's no one way that you can prove that an input program the computer will take the inputs and run and give an output. It might run forever, and therefore won't pause. That's something that's very important property of that, which is the one that he was interested in. So what this basically means is that you can never know for sure whether you have a full complexity because there might be a non-halting program. You wait long enough, will eventually halts. And so formally, you can't really dispute. Intuitively, right, if I have a string like this one, which looks pretty complex, is Borel random, in this case, the same Borel, different words, right? So it satisfies all the randomness tests, but it's actually pi. And so it has a short description.
Understand, you generally allow polynomial overhead.
Yeah.
Right. Whereas
here's not polynomial, here's it's order. The reason it's order one is because the amount I need to go from one universal relation to the other is independent of what strings I'm giving to it. So it's called order one term. It's basically a fixed term, fixed cost.
I know you don't want polynomial ambiguity, but let's say a Turing machine to another Turing machine. Those equivalences are generally polynomial.
Polynomial in length of processing, but they're linear.
Why not define complexity using a quantum computer? That's our point. Something that exists in nature. What tells us that we should live in a classical universe?
It's not a, we should probably raise that. So actually, people have looked at generalizations of this quantum computing, but right, there's a long complicated story there. Anyway, this is interesting. So one of the things that you can see from this is that what's a random number? A random number is a number that has no short description and print the number, right? That's what's basically going on. And so one of the interesting things about this is you can think about this in the algebraic monkey theorem as follows. What if I just have a universal Turing machine and I randomly give it programs? How likely is it to produce an output like that? And interestingly, historically, it was Ray Solomon who came up with this idea before Kolmogorov. And he was asking this question, where I randomly input into binary code into a universal Turing machine that reads binary code. And then the probability that I get a certain output is 1/2 the power of the length of programs that generates outputs. And the largest term in that sum of many programs is the shortest description, which is Kolmogorov. So famously, he predated the Kolmogorov, gave him credit, but because Kolmogorov was so famous, that's the name that he stuck. I have a quote here from Minsky, which says, since the most important discovery Gödel was discovered by James Solomon and Kolmogorov, the constant called probability. So this is the probabilistic version of Kolmogorov complexity. How likely is to get a certain output on randomly typing into a computer, into a universal Turing machine? It's exactly the algorithmic monkey story, right? So monkeys typing into a universal Turing machine, that's what they're formalizing here. And it tells you the probability that it's going to be at least 1/2 to the power of the Kolmogorov complexity if you have minor inputs. And really interestingly, David Levin, who's also known for P versus NP, proved that that is not only a lower bound on the probability you get, but also it's an upper bound to these kind of similar order one terms. So that means two terms that are independent of the string that you're actually trying to look at. And this is a very strong result. This tells you that on randomly putting codes into a universe true machine, I should expect an exponential difference in the probability that I generate an output, depending on whether the output has a local complexity or not. That's a really strong, powerful result. And you may wonder, why have we all not been teaching this in our undergraduate physics classes, given this is a very powerful result of the world? And the argument is, well, first of all, this only works for universe true machine. In fact, this proof only works if you have a halting problem. If you don't have a halting problem, the proof, you get the proof. No one succeeded in proving everything's got halting problems. So that's problematic. Local complexity is uncomputable. That's problematic. It only holds in the limit of these. There's order one terms that we don't understand and we can't bound. We don't know what they are. But being physicists, that's not going to stop us. So we might want to try to do it anyway. And the other thought is, if you look at, there's a famous hierarchy in computer science where you look at machines, and so universe true machines are these magical, amazing things that can do anything with tapes. But there's a whole series of other more simpler machines, all the way down to regular things, which are things like Markov models, things that just remembering. And one thing that Chomsky is famous for, long before it became a kind of certificate or lots of other things, is a very nice piece of work showing that there are these different classes of grammars and you can map them onto machines. And people look at that for neural networks as well. So, for example, interestingly, because you need infinite tapes, we don't think that recursive, so the RNNs are could be universal if they had infinite amount of memory, but they're not, so they're context sensitive. If you go a bit simpler machines, stack RNNs, regular grammars, which are the simplest grammar, actually transformers are much less powerful than a bunch of other in this Chomsky era. So this is kind of interesting because it tells us that these different networks fit on different parts of the Chomsky hierarchy, but apparently how that makes them perform doesn't matter as much. And so we could also ask ourselves, do these different classes of machines, different classes of power, also have something like a coding theorem? So I don't know how to prove that coding theorem for these. But it would be really surprising if that really strong exponential preference for simple things would fall away the minute you don't have an infinite memory. That's what I mean. So that's basically my intuition. So actually with some students, we spent quite a bit of time trying to prove another bound. So we got a typical physics heuristic bound, which says for input-output maps that are relatively simple, so where you don't need a lot of information to describe the input-output map, we think the probability that you get a certain output should be bounded by 1/2 to the power of the Polar complexity, which we don't know. And we're going to approximate this, being good physicists, by some compression techniques. So this K triangle is some computable measure of the complexity of the string, like zipping it or something else. And then I'm going to put a little prefactor in front of it just because I don't know whether I might be overcounting or undercounting. And I have some offset because there are order one terms that I don't know what they are. And hopefully I can hit those really quickly and see if that works. And so that's what we've done so far. It's not very mathematically rigorous, but it seemed very reasonable to us. And then we've tried it on a whole number of different systems. So to show you a number of them where it's worked extremely well. So this is, I'll give you just two examples. One of them is the folding of RNA. So RNA molecules are like DNA molecules, not 4 bases, but they can fold into well-defined 3-dimensional structures. They actually do a lot of things like catalysis or structure in your body, and that structure really matters. And so you can ask yourself, if I get a random RNA sequence, what structure is it going to form? And it turns out that if I pick sequences at random, it's exponentially more likely to make simple structures than complex structures. That's one example of how this works. So you can think of it as a whole bunch of other input-output maps of that nature that all have this property, which is if you randomly pick inputs and you ask yourself how likely to make particular outputs, you need a many-to-one map. But that's not the case that we have. And then you'll find that simpler things are more likely to appear. So here's a model for scaling rhythms, which is a bunch of 10 coupled differential equations. And if you randomly pick the parameters of that, you're much more likely to get simple than complex.
You said I missed it. In the RNA case, how does the overall complexity correlate with the ability to fold?
So they all fold quickly.
Right.
Yes,
This is biological.
Biological. So they fold. This not like proteins. These are easier to calculate. They fold. They all fold. And what you can then ask yourself is, will they fold into a structure like this one, where basically you got nothing folding and a little hairpin like that, which is pretty simple. This one is really simple. or some more complicated structure. And it turns out that they're exponentially more likely to find simple physical. What's also super interesting, which I didn't call growth, exactly. So in this case, what I actually do is you take that folding structure, secondary structure, which is who binds the glue. You can write that out as a ternary string and zip it. And that really tells you what's actually kind of very amazing about the RNAs is that if you look at natural RNAs, so the RNAs that we find in our bodies, then we can predict how likely you're going to find one by how it tells you how likely they're going to be there.
If you have random RNAs, do they also?
Yeah, so these are random in the sense that they're random sequences, but random sequences are much more likely to find simple structures rather than complex structures. Yeah,
with respect to folding?
They folding, yeah, they fold to simple structure than simple structure than complex structures.
You can it's different from protein to RNA.
That's right.
You're saying it's different between protein.
Proteins are a more complicated story. So it's a different story. But very roughly, so it's still true that if you look at the space of all possible RNA folds is very, very large. But the ones that nature uses is a very small subset. Those are the ones that are highly possible. I'll get back to this in a minute because what this is telling us is that the natural RNAs that we see in our body are ones that are homegrown. This is interesting because this is a inductive bias that nature has. In this case, these folds are enough. I'll give you one other example that I like. Zohar got a paper with lots of public attention because somebody wrote it again on, are we living in a simulation? So I had a paper that I wrote, but I think it's quite a fun thing. We looked at protein complexes. So proteins are very important molecules in your body. But half the ones in your body form complexes. They form dimers, trimers, tetramers. Hemoglobin is a tetramorphic compound. And they do that by evolving patches that make them stick to each other. And you can ask yourself, what symmetries are you going to find? We look at natural proteins have a lot of high symmetry structures. They tend to be very symmetric. And the question was, why is that? The intuitive answer biology will give to you is that because symmetry has some function. So nature looks for symmetry because symmetry is better. We make you show that actually, if you think about this algorithmically, what's happening is you've got a self-assembly process. You can work to write that out as a kind of model. And then it turns out that it's much easier to assemble things with low complexity than high complexity. And symmetry is low complexity. For example, if I want to tile this space, it's much less information to tell you take this tile and repeat it n times than if I tell you where every single tile goes. It makes it all different. And so that's a very simple argument. The only reason I'm putting this up is because I got attention for it because my student who's very good at these things, like me, I wanted to write something about, I want to say something about what I thought was really important about bias and algorithmic information theory. He started it with like from sunflowers to starfish, symmetry is everywhere. And that first sentence is what got it around. Not really the interest of the paper. So that's just a little sides to what we live in today. So that's the simplicity bias that we saw in those neural networks, which turns out to recapitulate the simplicity bias that you see in the biological systems, for example. So maybe that's why they work well in the kind of systems that we typically use them, because these systems have been somehow generated by some higher order models, high simplicity. That would be a very vague and unprovable hypothesis, but that's something that I think is probably may not be true. So that if this is, on the other hand, people said to us, okay, these neural networks work well on these simple, but maybe simplicity bias initialization has nothing to do with the fact that SGD finds this. Maybe SGD is finding these solutions for a different reason. In other words, if you were to take a neural network that didn't have that simplicity bias at initialization, maybe it won't. Maybe it will still find the same solutions as the neural network did in the standard way. So the question is, can we break that simplicity bias? It turned out to be harder than it looks. Because everything we try, the simplicity bias is quite a strong effect, and we see it all the time. But there's one trick you can do with neural networks that some of you may know is that if you take TINCH or ERF, basically continuous activation functions, and you initialize them with a wide enough initial width, you can get into a regime which is called a chaotic regime, where basically your output score is positive and you lose all memory your data, basically. And this is helpful because if you have these and if you get it very deep, so the deeper you make it, the more you feel the chaos, basically. And the wider you make it, the more you feel it. Whereas ReLUs don't show that quite the same way. And so what we always do with them is by making the initialization wider and wider, or deeper and deeper, that simplistic bias initially got started to fall away. So this is interesting. So we can make this become less bias. So for Mr. Occam's razor starts to disappear in the story. And this is not prior versus rank. They're still much more likely than random chance, but they're starting to become less biased. If you look at this probability versus complexity that I showed you before, you see again it's becoming less biased. And then you see something interesting, which is that with relatively small, with the bias going down to about here, so like that. So you're still, compared to random, where it's 10 to the minus 38, you're still 30 orders of magnitude more biased at the beginning than you would be for a random learner. You see that your learning generates dramatically. So your SGB converges to really poor solutions. So here you see that even on very simple blocks, like everybody 0, everybody 1, you get 35% error. And that's basically what's happening here. And the question is, why is that? Well, here's another thing that's very basic about AIT or strings in general, which is you can ask yourself, how many of those doctors, for example, are simple, how many of them are complex? So one way of thinking about that, how that counting works, is think about an ideal compressor. So let's say I've got an ideal compressor that for some magical reason can compress everything. It's therefore got to find short descriptions of the strings, otherwise it has to compress them. So let's say I take all strings of length 10, 1,024 of them, and my magic compressor can compress them. Right? Turns out that there are only 1,022 strings that are shorter, so 2 strings can't be compressed at all. 512 are just 1 bit shorter, so that's half of them, a little over half can be done by no more than 1 bit. 2 bits, 3 bits. So the number that I can actually compress by more bits is really, really small. This is actually true. The fraction I can compress by n bits is 1/2 to the power n. This also tells you that if I take a book and I zip it and I make the file from to half the size, right? Then if I count how many bits I've made it smaller, the probability that a random string of that length would be compressed by that much is 1/2 to the power. So an imaginary large number. So the kinds of things that we typically use are unbelievably unusual compared to random strings. So if I just want to calculate the prior, how likely am I to get a string of complexity k, and look at all possible strings, then that goes as 2 to the power k. This k is my magic complexity that I have from some magic compressor. So this right here that you see is how many strings you have of complexity k for this particular problem, like 128. You see the vast majority of them are complex. In fact, 50% of them can only be compressed by 1 bit, 75% by 2 bits. Now, what's interesting is that's 2 to the plus k. My AIT coding theorem bias is 2 to the minus k. So although the number of strings of complexity k grows to 2 to the plus k, probability I get a particular string grows to 2 to the minus k. So those two cancel each other. So the probability that I get a string of complexity k is going to be flat in that direction. Is what you see for a normal network. But if my normal network is slightly less biased than 2 to the minus k, like 2 to the minus 0.9 k, then I get overwhelmed by this growth of complex functions. So that's what you see in this one. Actually, that chaotic one goes way up. So it's basically finding all these complex functions. So why is this neural network, this red one here, generalizing badly? It's a classic variance problem. Exactly the problem that people were worrying about in the classic textbooks, which is because the number of functions grows exponentially with complexity, if you are not biasing just the right way against that 2 to the minus k, then you're just overwhelmed by the very large number of functions that can fit your data, that give you something wrong for the rest of it. So bias specificity is a very special bias in this case, because you need the 2 to the minus k bias in order to overcome that 2 to the plus k growth of number of functions with complexity. That's the only way you can learn these simple functions. Got it?
This is assuming you have no error. Like rate distortion will tell you that actually it's much better.
Yeah, this is no area. This is a very simple fact. I picked this discrete function because I can count it, right? And then a continuous function, but something similar must be learned. And so this is something interesting. So here I've got the complexity from 0 to 168, 160 because that's what my local zip compressor does. And you see that my neural network does well on these simple functions, but that's what we're using the last ones. There's a very famous theorem called no free lunch that based it from David Wolpert and others that basically says average over all possible, in this case, average over all Boolean functions, okay, no inductive bias is going to work better than any other ones. In other words, my neural network, if I try to learn every single possible Boolean function there is, can do no better than random chance. But here it looks like it's doing better than random chance for most of them. That's because I'm fooling you a little bit because I'm running complexity here. And the vast majority, 50% of the functions are right here. So what I know is there are some functions here where neural networks are doing less well than they have to. what this is telling me is there's a tiny, tiny, tiny fraction, exponentially small fraction of Boolean functions I can learn, and those are the simple ones. The rest of them I can't learn. And so if neural networks are doing well, if this is sort of true, then they're picking this really small subset of all possible neural networks. Those are the ones that they're learning. That's the basic takeaway of this trial. And this is like an Ising model. It's a very simple problem. It's much simpler than the more complex problems that we typically care about. But all I'm showing you is that there is an intrinsic algorithmic monkey coding theorem bias against complexity which you need to overcome the growth of complexity. Otherwise, you're going to get caught by the variance problem. The learning theory has been worrying us about for a long time. So that's basically the story there.
And also, so learning an algorithm which has that we can code basically should be simple then.
Yeah. Well, if I just pick algorithms at random, and so basically if I'm trying to learn this thing and I pick doctors at random, then I have no reason to know which one I can pick. But I pick algorithms that generate doctors, then I'm going to more likely pick simple algorithms than complex algorithms because they're just shorter algorithms than longer algorithms. And so therefore, I'm going to be more likely to get doctors that generate by shorter algorithms than longer algorithms, just because they're easier to find.
But in terms of scale, say I think about dynamic programming, so I can probably write that, in I don't know, with 200 tokens of code. Would that be in the regime that's learnable, or that's going to be astronomical? For do you have a sense of scale here? Or what is a truly large K?
What's really in terms of what these Boolean functions, yeah?
Yeah, is K larger than 100 already astronomical, or is
well, so if they're so in this case, if K is this is binary case here, K is 100 is 2 to the 100 possible functions, yeah. Which is unimaginably large. Wow, that's 30 basically. So all this. So this is saying something interesting about neural networks, which is back to that question that I had earlier. Is well, it tells me that basically I need this very special inductive bias, in that our neural networks have a special inductive bias of some kind. This is just one inductive bias that they have. I think this is a useful one for these kinds of problems. Does this generalize out to the other problems? Like if I'm learning something like image classification, it's much harder because I don't really understand what those functions exactly are. And they're functions from pixels to data. But what I do know is, this is back to your question, was if I look at images and I ask myself, how many possible images could you get? Well, it's unbelievably large, and the vast majority of them are not going to be interesting images. So even if I look at images of geographical data, those are still very much in this area of the set of all possible images. And that's why when you look at images like the famous MNIST, right? We know MNIST is 784 dimensional space, but the actual images are in a very, very low dimensional. That's true for all the images that we can learn on. So that's that we know. But the images that we care about are very, very, very special if I look at all possible. Because the vast majority of those are noise. So I basically made an earlier question that maybe we need a new statistical learning theory based on the bias. I think that theory is coming out. Arguments about kernels, things we can see even in linear regression. And it might be that actually one of the really nice languages to do that well is field theory, where you go beyond just linear regression, which is something interesting. That would be. I think there's a gap in the market there still for pedagogical text. And then I asked myself, I gave you one example, which is simplicity bias, but I think the really interesting question is, what are the other inductive biases that really aid generalization? So you just had a very nice talk about equivariance. And that showed that if you could build some of these biases in, basically some symmetries in, that can also help your generalization. So something like that is true. But basically the story of neural networks, the story of high capacity models is a story of inductive bias. To understand what they're doing, you've got to understand what they're biased to and what they're not biased against. And anytime you start asking yourself, what could they do? The number of things they could do is exponentially large, unimaginably large, compared to the things that we want them to do. And the really mystery is why, when they do pick things, they pick things that work so well. And simplicity is just one very crude way of looking at it, but it can't be that it's only part of the story for sure. And I think, as I said before, this is telling us something about the natural world. Things that we care about have some special properties, very special properties. And maybe we'll actually learn what the special properties are by figuring out why neural networks can remember. So if we can learn a really good understanding of what the inductive biases exactly are, then we'll also maybe learn something about why certain mathematical problems are solvable by neural networks, because there's some structure, hidden structure in those problems that they're exploiting. They sound naturally exploit. Why these dumb, models do that is completely mysterious. So far, we've question 1, why do neural networks generalize at all? I'm going to look a little bit at question 2, given a neural network, can we make it better? Now I'm going into a regime where I really understand, and my students are continuously confused me. This may be a better way of saying it. So I just want to talk about feature learning, which we've talked about a few times in this talk. And feature learning is actually a not well-defined term in the deep learning community. It was a well-defined term in early days. So actually the first example of features is by famous Fisher, founder of modern statistics. Actually, his paper was looking at these 3 different kinds of irises, and could you, by taking a few measurements on them, distinguish them? And so he looked at the sepal side, length and width, and the petal length and width, 2 different parts of the iris, and these 3 irises, and then he basically, if you look at those 4 different properties, you can distinguish these 3 by how they cluster. What's interesting, by the way, is that one of them, the one in red here, which is the setosa, is clearly separated entirely from the other 2. The other 2 kind of intertwine. So this is the first kind of example of features. So when you do features, you give those features to somebody. So I look at these computed images, I extract features, and then I use those to classify what basically are. For a long time, that's what machine learning people did. They spent their time trying to figure out really clever features. You need a lot of domain knowledge to know what those features were. And this is why, so when people have feature learning, it was the fact that you had to learn those features. It's amazing with neural networks, you just whack those images into the neural network, and it somehow extracts something that is learning some kind of automatic feature detection. So that's a very important aspect of what neural networks do well. When we talk about feature learning, often we're trying to understand, like, does it effectively just look at the sepal and the petal length and width, or is it doing something else? That's the kind of question that we're trying to answer. I'm going to take a little aside here. This is a moan, because I don't see this as much in the overall neural network, which all has problems, but in the quantum neural network, I'm sure the stuff is a bit crazy. So I recently wrote one paper on quantum neural networks, never forget. And my students were very excited about this paper, the power of quantum neural networks. This group from IBM cited 900 times in the last few years, so 350 times last year, increasingly important talk. They basically showed that this quantum neural network, which is this black line here, outperforms the best classical neural network we could find at the same size. So it's an 8-node quantum network. So that's fine because it's hard to make quantum network. Just pick an 8-node classical neural network. That's a fair comparison. And look, it does much better on this data set. That's what they said. And so I was looking at this, and I didn't notice something that I should have noticed, which is that their loss only goes down to 0.2 instead of 0. Okay? So my student Chris went into the GitHub, because they didn't actually say in the paper exactly what part of this data set they use, or exactly what neural network they use. And it turns out that this is a neural network that they use to compare with. Okay? And what they actually learned on was only 2 classes, not 3. The question was it red or was it blue or green? Well, then I just make a straight line. Okay? I put a straight line through there, straight line there. If you want me to figure out what is like the petal length and sepal length, I just put straight lines. That's a completely trivial problem to solve. So then it was even more confusing. Like, why did that not work? Well, if you take just a perceptron, which is a 1-layer neural network, it's a 0 training error. If you allow your axis to go down to 0, you should. It's 0 training error. So I'm just putting this as a moan, right? And the amazing thing is this paper has been cited 900 times. I'm putting it up because actually a student was in the group that I inherited a student from had spent 2 years trying to work on something inspired by this. And that's just that. So, like, this is one level up from, I think, stuff we see in CNN, which is crazy. So this is the moan, because that's how I learned about the iris data set. All right. So what my student Yunsu started asking is, can we think about this picture of neural networks as feature learners, as automatic feature extractors, and see what that does? So I have some input data, then I've got a bunch of layers that are basically learning features. There are filters or something that then I feed to my final linear layer, so my final linear classifier. And let's say if I got C classes, then this final layer, the class that is the correct class will light up. And if you look at a lot of the early pioneers of neural networks, that's how they thought about it. So you've got a bunch of, in the CNN, you've got a bunch of convolutional layers that are somehow trying to automatically learn features. So that just like in Fisher's case, you end up with a small number of parameters that you can easily put straight, separate with a linear classifier. So that's the model that we're looking at. And another way of thinking about this is, as Boris said this morning, classical feature learning is you've got some function which expands in some features, right? And those could be something like petal length, subtle length, or a more complicated function. And then you try when you're learning is just learning the coefficients in front of that linear. That's the classic old-fashioned feature learning language. And you can think of a neural network exactly that way, where you say, okay, that the feature that function right there is basically what happens to my data as it propagates through these different layers before it's given to my final linear classifier. So you can basically, what you do is you say, let me look at what comes into that final layer classifier, what functions coming in, those are my features. And if I have p layers, I've got my final layer is p wide, I've got p functions coming in. Does that make sense? That's very simple. So what you can also do, by the way, is you can make a neural network and freeze the layers. Okay? So there you don't learn anything, you just freeze them. And then you have your final layer and you learn. It's a random transform. So you give a random transform. And I'll give you an instance, because and this is actually quite a simple problem. Here's a CNN, 5-layer CNN, where we freeze everything except for the final layer. And then we ask, as a function of the width of the final layer, at which point this blue line is a training error, you get 0 training error. So at which point with this random transform, can you actually learn that data? Can you, to 0, can you learn all the labels to the images? And it turns out that in this case, at about 1,000, it works. So then that's interesting, which is if I have a 1,000-wide CNN, then I know that there exists a solution, gives me 0 training error that I can train to, that is basically doesn't change the weights at all. It only learns the last layer. So I'll call that like a frozen feature model, but that's the thing I'm going to try to contrast my problem. So if I have 1,000 of these random features, I can learn MNIST. I can write out functions, I can get 0 training error from this data set. So I can give it, first I'm going to give in this kind of picture, I'm going to do a toy model. Okay? And I won't tell you the details of how we work out what these, but you can basically look at that final layer, you can work out what those functions are by using classic standard techniques. And you can then ask yourself, what is that final layer doing when it's given some particular function to learn? So here's a neural network on a very simple problem, a Heaviside function. So it's a one-dimensional problem where you've got a Heaviside function and you're asking it to learn that. This is at initialization, the first 1, 2, 3, 4 eigenfunctions that neural network shows. And it turns out if you take those eigenfunctions, I think I ended up using a wider. This is an old picture, so it's now using a width of 1,000. If you do 1,000 of these essential functions you get at initialization, you can fit that Heaviside function to 0 training error, or low enough training error. And what the neural network does instead, as it trains, and it doesn't kind of learn the prefactors of these, it actually learns a new eigenfunction. So the final layer, which is the first one, which is just the Heaviside function. So it's actually learns so that basically, if I write that final layer as a linear function, rather than picking all those functions, learning the coefficients, it actually learns the feature. And that's what's called feature learning. In this case, it's a super simple, I think this is, again, an Ising model of feature learning, a very simple problem, and it actually just learns this Heaviside function. It's kind of surprising. Why does it do that? It didn't have no particular reason to do so. It could have learned all the coefficients. Right. So in order to think a bit more about these, what we're going to do is define a few order parameters. So one of them is if I have a set of eigenfunctions, so eigenfunctions of my feature map, my forward feature map, the ones that are fed into that final layer, I can look at something I'm going to call the quality, which is how well does, for C classes, does a particular eigenfunction that I learn fit onto my true function, my true function. So my ground truth function, the function that describes my radio. And then I can project onto the target function over all those eigenfunctions. I can basically look at how well have I learned my final target function as I go through all my different eigenfunctions. I'm going to order those eigenfunctions by their eigenvalues. I can do that for how well I project onto my true function, and as well I can look at what my neural network actually does. So what's the function that it actually learns, and how many coefficients has it used to effectively learn that. And what you see is this, for example, for that CNN example. So remember I gave that CNN example, just slightly more complicated than this heavy side, but I'm going to learn MNIST. I can do that with a frozen layer. So I just learned that all I'm learning is the final. I don't learn any new features. And then I see that I use, and this is on a log scale, I use basically all 1,000 features in order to accurately represent my true function. But my neural network actually does something very different. It learns new features. In fact, it only learns 10 features because there are 10 classes in MNIST, the minimum number I need, and that's it, it's learned 10. If I look at, this is compared to the true function, this is what the function that it learns. It also has picked, instead of using all the functions available to it, which is a perfectly suitable minimum, it picks a different minimum, which is a minimum where it only uses a minimal number of functions. It's done something quite dramatic. I think what's kind of interesting here as well is when you're in the infinite width limit in a Gaussian process, you're basically doing a wide version of this. You've got frozen layers, and you're therefore doing something analogous to learning with a very large number of functions. But this thing is actually collapsing down to a very small number of functions. And in another language, this is called neural collapse. You get that long times. So it's just something that's worked out by Popyan and so it's kind of interesting. Why does neural network do this feature? Why does it behave so differently from how it could behave? Like, why does it not just freeze its inner sight layers and learn use something learn? Why does it pick this minimal representation?
Kind of, are you using mean scaling here, standard scaling?
This is standard scaling. I know we've not used UP in this case. So I don't know the answer to that question. Why? I'm noting. And so I just worried that this kind of collapsing to a minimal number of possible features, we call this a minimum feature regime, happens for 10 classes, 20 classes, 100 classes. You see that very clearly. I'll show you, if you look at with time, so I'm going to show you here, this one is the C410 with a ResNet, which can walk you through this first one. This is how well you map onto the true function. So after initialization, you need all of your functions, and you should not do that well. But then, as you learn, after one epoch, you've already picked a much smaller subset of functions you're learning. So very, very quickly, this neural network aligns with this small subset of things it wants to learn. And after, by the time you get to convergence, in this case, this is 95, close to 95% accuracy on C410, so it's just 200 steps. So what you see is that this neural network has learned quite quickly. It's aligned itself towards this minimal feature regime. This is interesting. Why does it do it so quickly? And why does it not use its eigenfunctions, its features at initialization?
Is the number of minimal features equal to the number of classes?
Yeah. So what you saw here, 10 classes, 20 classes, 100 classes, it always picks exactly the number of classes, which is the minimum it can do. You can't do that. These features are the eigenvalues of the forward feature map. So it's the map of everything it's what you're mapping into your final layer. So if you write your
This is like standard stuff for us.
yeah. It's not the first person that looked at this. It's the obvious way to define a feature, right? If I think about features as a neural network as a bunch of transforms that I then feed into my final linear layer. And the question is, what have I fed into my final linear layer? Then I can look at what those eigenvalues are. And that's the functions that's one way of looking at what functions I'm fitting in. So I order them by here we order them by their eigenvalue. And the first 10 are the ones that you use if you've got thin loss. The first 100 if you have C4.
It's not saying the distribution, saying the kernel has like high angle. So this is like, this is like, wait, so like, this is a standard, this is like when you decompose, for example, the Hessian for, and then you have this term that has a number of.
Yeah, it's great. It's basically telling you that, all it's telling you is that the neural network is doing something very different from what it would do if you didn't train. So the reason I'm saying that is, I was just telling you that without training neural network, just initialization, I get simplicity bias, and that's all something I don't really train at all.
The thing that I may be saying is that like even if you think of it as the kernel regime, like a lot of the smaller eigenvalues are still involved in learning, but the large ones are there's like just like some degenerate reason why there's this.
Well, so in the kernel, so in the kernel, you know, so if you took this MTK kernel initialization, you would not use. You would find that you would use only a subset of all of the so that subset would be larger than that. So that's different. And so that's a story of not that story. So it's not the same story. I asked my students the same question the first semester. No, sorry, they're totally right. What's actually interesting is if you take an FCN on CFAR10, trains zero training error, it's unable to get this minimum feature regime. So we know FCNs don't generalize very well, but also we see that we train it and we're unable to get it into a regime where it only picks 10 functions, it picks a lot more functions for reasons we don't understand. This is a classic thing that we see. So typically we see that neural networks generalized well tend to have this collapse to a small number of minimum number of features. That's not always true. I'll show you a few other things that we see. So I showed you in that bound example that you have these nice power levels with a mini orders of magnitude for the number of data points. Pretty simple data sets, but CFAR10, remember I told you was bending. I said I'd come back to it. So here you see that. So this is basically a Gaussian process up to 50,000 data points. That was a very expensive calculation because the Gaussian process is very slow. This one here, this orange line is the neural network trained on exactly the same data. And you see that it basically follows the same scaling with number of data points as the infinite width neural network, which is equivalent to like this coefficient learning regime, where just learning coefficients with frozen features. Then at some point, suddenly it deviates and starts scaling with different scale. And the question is, why is that? This blue one is here because it turns out it's much easier to train these things on data augmented data, which is what we're doing today. What you kind of see interestingly as well is as I look at how well this is making a projection onto the true function, you see that as I look at 100,000, 5,000 data points, between 1,000 and 5,000, you see a sudden jump in how well accurate. That's basically also where I start to see this high point way down. And so now I'm overlapping much better with the true function. And we have a measure here, which is basically, this measure is looking at the kernel that you get at a particular time and seeing how well that kernel overlaps from the central kernel line. It's an alignment measure that says how similar to kernels between the kernel that you would have for the perfectly the minimum features, where you only use the minimum number of features. You can write that kernel down analytically and work out how similar you are. And we have a heuristic that says basically when that is about 10, when you're at 10%, 90% of the final kernel will say that you can converge that machine. And you see that roughly speaking, where that suddenly changes is where this kernel, where the kernel starts to really change. It's roughly the region at which point you see you're getting this feature learning, where you're suddenly learning better. So you're in a regime where you need more and more data to learn better, and suddenly when the feature learning comes, you start going down. So that is linked to feature learning some way or the other. And the question really is, how is that linked to feature learning? We're not entirely sure, but we see it. Interesting, my student Nick, who's sitting here taking this project over, has shown, which is probably surprising to me, the audience, that if I take other data like a staircase function, one of them, multi-index function, these are functions that are chosen because we know that kernels can't learn them. So we can prove that, for example, how much data do I need to learn them that grows exponentially for kernels, and it does not grow that way for neural networks. Here, what you see is, as you increase the number of data points, at first you'll see no difference with the NTK kernel, which is the initialized kernel. And then suddenly you get this enormous drop in error, so gain in generalization accuracy, which we see and don't understand, but we think is linked to feature error. So we think what's happening here is something like what you saw for the heaviside function. Some of the neural networks realize, oh, I can learn a new set of representations. They're completely different from the representations I had at the beginning. That, in fact, in a different Hilbert space than I was. My initial Hilbert space didn't have that function, that now it does. So it's learned that. And we don't know why. But all we're saying is this story is something really interesting.
What's the input dimension again?
Nick, what's the input dimension?
So the staircase functions, it's 13 input dimension, but the staircase function only depends on 7 of the purpose. And for the right nodes.
So it's this. This is where I'm. Nicholas is going to educate me on this. Hopefully, figure out why students. But I think it's super interesting, right? There's neural network here as a really good example where it's learned a completely different representation.
I mean, I would expect that it can learn the linear component at a roughly m equals t, but that doesn't fit.
Yeah, no, it's not quite what we see, but that's what we're something like that. So I think this is here. I'm in very recent kind of results where we don't understand what's happening. Obviously, in this feature learning can be quite strong in neural networks. I think,
but it's standard scaling, so there is also an n in the observer. Well, we talk about that.
So one of the things is
pushing it might be like 7 times 400.
So Nick has been telling me, actually, we've been spending all this time looking at image data. You spent all this your life looking at image data so far. Maybe image data is a bad example of what neural networks. So maybe neural networks just are almost like kernel learners. Maybe all that whole story about initialization tells you a lot about what happens is only true for this data set. Maybe other data sets are not that way. And the fact that neural networks do well on them is because they've got this extra bag of tricks, which is called feature learning, where it somehow knows, for reasons that are completely opaque to me, how to learn representations. I mean, we had some really interesting hints from Daniel and from Zohar about how that might happen. I think it's one of the big mysteries that we've got left in front of us. Last, I'm not going to say more about this. We looked at a lot of things with this. You can learn a lot of things like what is batch. So what you can learn, for example, is what you can learn when you don't know it does badly. So you can also use the same projection on earlier layers. Right? And what you can learn, for example, is that very famous example is VGG, which is a network comes here from Oxford, very deep convolutional network, very, very popular. It's known that if you don't use batch normal on it, it generalizes really terribly. It goes completely haywire. And what you can see is what it actually does is it doesn't do that on minimum feature learning. In fact, it tries to learn everything in earlier layers and gets stuck. So if you then, the batch norm somehow distributes some of the learning over the different layers, that's really good. And these kinds of, this is a measurement technique where you can see that's happening. So you can see that's what's happening. Empirically what's happening in batch norm, why batch norm does it, why that's good, is it clear? But intuitively, if I have a neural network of external layers, I want to kind of intuitively learn roughly the same amount on each layer. I don't want to overload one layer with learning and not learning. I can do things like greedy learning, where I learn every layer to its maximum, minimize layer by layer by layer, rather than minimize all layers at once. And then you see that you get collapse in early layers. And that's not good because your early layers actually need to be more expressive. And the final layer gets nice. The last thing you see, I think, which I think might be interesting to some people in this room, is in this very famous paper by Shizat and Bach, where they looked at what they call the lazy regime. The way they generate the lazy regime was by multiplying the target function constants. And so it turns out if you do that, then they say you enter the lazy regime. But essentially, if you look at these, if you look at this particular problem, which is just creating FCN of 256 on MNIST, then the really lazy regime, which is where you freeze the layers, right? And that final layer isn't wide enough to learn it. And so you get this, you use all 100 or use all 156 functions, but you don't end up generalizing here. Oh, that's truly lazy regime. No matter how much you multiply that last layer by, you always end up in something which is much more like a feature learning. I'm saying that just because some people have used this as a trick in order to get the lazy regime in the learning. But it's not the lazy regime that we might think of not feature learning. It is feature learning. It's not feature learning very well. So that's the advantage of this kind of method. I don't understand what's happening, but I can at least measure it. And this is it's like the dumbest way, I think, to measure features, which is the way we thought about features as those are the things you put into your final linear functions. Let's look at them and see what they do. And what I see is they do all these interesting things that are very different from the infinite width limit, very different from this lazy, the true lazy like freezing. All right, so I come to the end of my talk, and I think here's some questions that is raised for me. First of all, how should we measure feature learning? This is one way of measuring feature learning. I don't think it's necessarily the only way of measuring or the best way of measuring it. There might be other more instructive ways. Zohar talked about a much more clever way of looking at correlations between outputs. Reactivations.
Especially for the final layer, it's the same thing. We're just looking at inner layers as well.
Yeah.
I would argue that you're measuring the adaptive kernel of the final layer. hearing that.
So maybe we should look at the adaptive layer. I mean, maybe. So I think maybe we're doing something more similar than I realized. No, it's interesting to think about. Why does a neural network do this? Why does it do this very strong feature learning behavior? It's kind of mysterious. It's interesting. The early pioneers of it really talks about it. That's how they thought about neural networks. Just a set of filters that learn features, and then I use them to do my inference. This is clearly what neural networks are doing. But why does that work? We try to actually analyze these features. So you look at the 10 features, you see something, and then it's obvious. That's obvious. Very clearly for AI safety, this is super important because this is what the neural network is doing. If I mess up with the neural network, I'm messing with its final features effectively. So I think this is something, this will tell us something about we protect these things against doing something bad. But we have to first understand why they feature learn and how do we do. I don't understand. And I think an interesting question for some of the theorists in the room is, can we perturb around this infinite width and decay limits and get to this regime, or just like a non-perturbative regime? And this, I think on images, maybe that we're fooled by images, and that on these more interesting data sets, actually perturbative methods are not going to get us. I think that's an interesting question that we used to try to tackle some of these toy data sets that we just showed you. And what does feature learning tell us about generalization? So the interesting thing is, I showed you, for example, a ResNet on C4 or a CNN on C4, it does this really strong feature learning. But we know that if I take the GP limit, the infinite width limit, and I look at that same data as the, so you showed that from the Google group, that it basically performs almost as well. So these are all questions that are mysterious to us. So that's the last thing. So you're doing something different, but it generalizes almost as well. So clearly the feature learning on its own is not the reason why it generalizes well in that case. In this case of the staircase function, it clearly is why it generalizes well. Something like as well. But it's really hard to figure out what that connection exactly was. And we found some examples where feature learned ones are slightly less good. I think that's going to be FCMs, right? So FCMs, we know the kernels are better. So why is that true? This is all my question now. So that's the talk. These are the people who did all the work. She's the one that talks about it. And thank you very much for your attention. I'm really good to follow the part of work.
K class classification will give you the freedom of K minus.
Okay.
For any K class classification, will give you the freedom of K minus 1 because of the protein normalization. I was confused by the number of features in your classes are the same. Is it
why is not one left? Why is not one left? So we use that.
Sorry?
So why is it not 9?
Yeah.
Because the organization will give you just one.
Yeah. So what I'm asking is,
I'm basically saying if I know 9, then I know.
Yeah.
When the 10th one is just the.
Yeah, so it's not learning to do that. Like it's kind of saying that even the 10th one is also kind of independent. And if I understood it correctly, or
yes, that is correct.
I mean, I'm just confused. Yeah.
Some of the Kolmogorov complexity stuff. So I know people in just energy landscapes generally, whether it's protein folding or machine learning or in cosmology, people are interested in questions about how sort of complexity in the sense of P versus NP relates to why we find certain types of states. I think, I mean, it just feels like this is totally different. Have you, for example, even maybe in the case of proteins, so we have low Kolmogorov complexity proteins biologically in us.
Yeah.
Presumably selected by evolution. Is it known why that is? I mean,
well, so yeah, so there's two different things. One is protein folds a particular 3D structure.
Yes.
And the question is that hard to find that structure or not? It's called Leventhal paradox, an energy landscape problem.
Yeah.
So you've got and the argument, this is Leventhal paradox. I have a protein of length, say 100, and each one has 6 angles between it, and I got 6 to 100 possible configurations. The longer the age of the universe to find it. And the answer is that it doesn't find it by randomly looking around, but it has to funnel against it that funnels it down. And if it doesn't happen, then it can't fold. Then it would biologically not. There's a different question is, if it does fold, what fold does it find? And that, for that one, actually, I've got a big project on it right now. I think we're showing that these are much simpler than you would get if you look at. So basically, I think length 100 proteins, they have all possible folds. There's a very large number of them. Then the argument is the ones that you're gonna that are more likely to appear on random mutations are the ones that are simple. And because they're more likely to appear as variation, they're much more likely to be selected for, because that's, so natural selection only selects on variation that appears on random mutations. So this monkey monkey theory is the same. In biology, what happens is you have random mutations. That's the monkey typing. That's a typewriter typing. But you are not your DNA, right? There's a development of the process that makes you. And that's also true for a protein that forms. Right? So protein is not in sequence. It's sequence then by an algorithmic process, which is basically the algorithm there is statistical mechanics. And that gives you a particular fold. And our argument is that when you type into the algorithm, the sequence like typing into a particular algorithm, that gives you much more likely folds that are simple than folds that are complex. So that even without natural selection, you're going to so random mutations are much more likely to throw up simple proteins than complex ones.
And the point of your common graph.
Yeah.
Correlated with things that have energy landscapes and other things.
Oh, that's a question where that would be a very interesting question that we're true. We don't know. Yeah. But regardless, so that one of the things to think about is that the number of possible. So how many sequences are there of particular length? So if you take every length 56 protein, it's a peptide, really short. There's 20 amino acids. 20 to 56, you made them, that would use up more mass than the observable universe. So these are spaces that are so big that they're unsearchably big. And so what happens is you're only searching a super small subset of that space. And the random mutations end up, what was really fascinating is you do find the same protein folds appearing independently multiple times. That would seem like magic. Unless there's a very strong bias to certain types of folds. And the ones you see that come out repeatedly are the ones that are easy to find. So what happens is, although the space of possible folds is unbelievable, it's hyper-astronomically large, the ones that are actually seen on random mutations is a very small subset of those. And that's all the nature that natural selection has to work with. The really deep question is, why is it the case that the ones that are easy to find are rich enough to allow nature to work? That's really amazing. So for RNA secondary structures, on say coarse grain measure, we've shown that for typical RNA lengths, between 100,000 and 1 million random sequences gives you all the secondary structures. That's a simpler description structure that you find in nature. And that means that basically, all that means is that all nature had to wait for was that small subset of random sequences in order to find the structure that it needed to do all the work it does in those. So that's why I'm kind of bullish on this idea that this bias of simplicity is giving us biasing our biological world to a very small subset as possible. And maybe something like that is also biasing our visual world or other worlds to small subsets of what's possible, and that neural networks have that same bias. Maybe that's why these biases align. But the fact is, these biases have to align, and that's mysterious. So this is really stuck into the late night, lots of beer.
Yeah, we should have that conversation. Maybe offline.
Yeah.
No one has several related thoughts that sort of went through here. So, they're trying to fit a neural network to Galavio manifolds.
Yeah.
There's trying to fit into materials that form, and then trying to fit into language. Right? So, if you fit it to language, the suspicion arises that, and one recent papers by Matthew Byard, like which we have that network inside our head which generates language, and then there's a network which sort of decodes it. So you could imagine that the network inside the head has a certain structure to it, that if you could invert that structure, which is what he shows for the simple case. So that's one. When it comes to things like proteins folding or something like that, right? So this comes to myself. Over the years, gotten fascinated by thinking about physics from the point of view of computer science, and then become unfascinated.
Okay.
Right. And one reason, so let me, in your case, for example, let me say, if the protein folds according to the physical process, I can certainly take the things which fold quickly concept of reasonable time scales will turn out to be important. Something that can fold over 100 years is irrelevant to our. But it could be that the one that folds over 100 years has some clever algorithm in the space of algorithms, because the computer you could get it to do something. Because the rules of physics are very constrained, whereas what we would define as an algorithm, can work in very different ways. So it seems to me like, so this is why I always get stuck with asymptotic results in computer science, because they actually prove using, stuff which is not necessarily spatially local, right? In the space of bits, it's often few body, local, but typically not spatially local. So applying it to nature seems unclear to me that there is that kind of simplicity, but just captured by the code. Flavion manifolds and other stuff. I don't know. What I can tell you is that there's a problem I've had for many years, which is this quantum satisfiability, where we were able to prove that quantum instances, which are defined by quantum Hamiltonian, actually are an underlying classical problem, which is all you care about is the graph, because almost any Hamiltonian you would pick randomly in that graph would have the same dimension of the downstairs space. So that struck me as, oh, this is great. Here's machine learning, and all I have to do is generate a training set and train on it, and it can tell me what the classical property is. One, of course, it's hard to generate a large training set, but I did at that point check with Jared Kaplan before his net worth went up by several, many orders of magnitude, so he had time to talk to fellow physicists. Time was cheaper. And when we discussed it, his view was this. It just seemed like a very subtle property, and it's a well-defined problem. So anyway, I'm just saying there's sort of various things in play, and the one I have the easiest time rationalizing is that same way as you can understand what I'm saying, even though you get Belgian or Dutch. We did discuss this. We did this because ultimately our brains are not so far apart, right? It's just whatever languages we were trained on. So that one I find it easiest. Everything else is hey. One last thing. There's an old paper by Eugene Wigner from the 50s, which is that ultimately either physics will be the most fundamental science, or psychology. What he was thinking was that your only access to the world, was